Okay, so everyone, remember I said that today we will be finishing up our kinematics unit. So there's one more thing we need to talk about in this unit, and that is how to interpret the areas of velocity versus time graphs. Um, and of course, once we finish up with that, there's a few more things I got to discuss, and then I'm going to release you guys so you guys can get started on your assignment, which is in AP Classroom. And I'm going to explain more details on that assignment at the end of the Zoom lecture for today. Okay, so let's finish off this unit, kinematics, which basically just deals with mathematical motion, using the tools of mathematics to be able to describe motion in the real world. And of course, this Friday and heading into next week, we're going to get started with our second unit, dynamics, which involves Newton's laws and forces. Okay, and I see some people are still coming in. Let me go ahead and get the link to the attendance form back out to you guys before I start sharing my screen. Okay, so let me begin by asking you guys a few review questions. So we've already talked about graphs up until this point. We talked about position versus time graphs, velocity versus time graphs, and acceleration versus time graphs. Okay, so if I focus here on position versus time graphs, so let's say you have a position versus time graph that looks something like this. Okay. Can someone in here tell me what does the slope of this graph represent?
The velocity?
Yep, the slope of a position versus time graph always represents an object's velocity. Guys, please embed that in your brains. That is going to be something that is going to be important in this course that will come up again and again. The slope of a position versus time graph is always the object's. Sorry, guys, I don't know why this screen is hard to write on today. Okay, there we go. Did someone send Jordan the attendance? So the slope of a position versus time graph is always an object's velocity. Always. Again, guys, this is something that, in the future, whenever I ask this question, this basically needs to be something that you guys need to embed in your brains. That as soon as I asked it, you guys should immediately know what the slope of a position versus time graph tells me. In this case, this object is moving at a constant velocity, and we see that because we have no curves here. So our object is moving at a constant velocity in the positive direction. What about a velocity versus time graph? If I give you a velocity versus time graph, it looks something like this. Could someone tell me what the slope of this line represents on a velocity versus time graph?
If it's never mind. Isn't it like speeding up or something?
Yeah, it is speeding up. It's speeding up in the positive direction. So what does that mean? The slope is our what?
Accelerating.
The slope is our acceleration.
Yes, sir.
Yep. So the slope on a velocity time graph is equal to an object's acceleration. Guys, please embed this in your brains. If I ask this on a future test or on a future quiz, this is something you guys need to know. That anytime you have a velocity versus time graph, the slope of that line is equivalent to the object's acceleration. Okay. And by the way, just to prove that to you guys, again, if I had to prove out my units mathematically, let me demonstrate that for you guys. You guys all in here know that slope, by definition, is equal to rise over run. Right, so rise over run. Okay, so we all in here know that that is the definition of slope. So again, I want to demonstrate to you guys that if I plug in my units into this equation, the units that I get as an output is my velocity. So along my y-axis, guys, I'm plotting position, along my rise here. What are my units for position typically? Anyway,
What is your what?
what are the typical units that we use in this class to represent position or displacement? What do y'all think?
Meters.
Meters, exactly. So basically, what this is saying is, along my vertical axis, I am plotting meters, which is my rise, and along my horizontal axis, I'm plotting time. And what are my units for time? Typically,
Seconds, right?
yes, seconds. So what do you notice? Slope is equal to what divided by what here?
Meters divided by seconds.
Meters divided by second. And clearly, those are our units for velocity. So, guys, on a test, if I ask you guys to mathematically prove to me that the units um, um, for velocity can be shown from a position versus time graph, this is what you would do. You would just tell me that if we take the slope of the line of a position versus time graph, it's equal to rise over run, or in other words, meters over seconds, which just gives us meters per second, which are the standard units for velocity. And of course, um, what about what about acceleration? How can I prove to you guys that if I take a velocity versus time graph, that my units will always come out to the standard units for acceleration? Well, once again, let me write this out. Let me kind of zoom in on this. So once again, I'm going to write this out. That slope is equal to rise over run. Again, you learned that in your math class. I don't need to hammer that point home too much. And so rise over run. So in other words, what's on our vertical axis divided by what's on our horizontal axis. So what are we plotting along the vertical axis? What are our units here for velocity?
Meters per second squared.
Well, just for velocity, for meters per along the vertical. I'm proving to you how to get the units for acceleration, Jeremiah. So the units for velocity are meters per second, right? And the units for time are what?
Seconds.
Seconds. And of course, you notice meters per second per second. What does that equal? Jeremiah, you just said it.
Meters per second squared.
Yeah, meters per second squared. So this is the mathematical proof that if you take the slope of a velocity versus time graph, which is equal to rise over run, in other words, what's on your vertical axis divided by what's on your horizontal axis, you get meters per second and then divided by seconds because time is along the x-axis. So meters per second divided by seconds, here you have 2 seconds there, hence you get meters per second squared. Okay. Does that make sense, guys?
Yeah, makes sense.
Okay. So guys, please remember this. Please remember what the slopes of these graphs tell us. They are extremely important. Okay. Now, we've already talked about this. We've already talked about the slopes of velocity versus time graphs. But here's something I want to introduce to you guys that's kind of new today. What happens if we take the areas of a velocity versus time graph? So if I have a velocity versus time graph and I take the area, what does the area represent? Okay, we already know what the slope physically represents. Now we're moving on to areas. Okay, so before I answer that question, let us review a few things from math. So again, along our y-axis here, we are plotting velocity. So velocity is being plotted along the vertical axis, and time is being plotted along the horizontal axis. Okay. And so everybody should know what this means on a velocity versus time. But if you have something like this object is speeding up in the positive direction. To be speeding up, to be specific, it's speeding up over an interval of 5 seconds because you see 5 squares here. So over an interval of 5 seconds, this object is speeding up. Now, the question is, I want to know, how do I take the area of this graph? And then after that, I want to know, what does that area physically represent? So first of all, let me draw out what I mean when I say I take the area of a velocity versus time graph. So, this time graph goes on for 5 seconds. So if I take the area of this graph at 5 seconds, uh, so basically I would draw a line here and a line here, and I shade that in, and notice I get something that looks like this. Okay, so I have a triangle here. So how do I take the area of a triangle?
A
Just,
equals 1/2 times space times height.
Pythagorean.
no, we're not using Pythagorean theorem. You're not finding the length of the hypotenuse, Jeremiah. We're finding the area of the triangle.
It's A equals 1/2 times space times height.
Exactly. Thank you, Michaela. I almost said Michaela again, but I caught myself, Michaela.
It's okay.
So yes, but you're right, Michaela. Area, and guys, this is something y'all need to remember, because we're going to talk about this a lot in this class, because we're going to be dealing with areas of graphs a lot. Not only velocity versus time graphs, but other graphs as well. So the area of a triangle, and I'm going to write this down. The area of a triangle, as Michaela just said, is equal to 1/2 times base times height. Okay. So that's something you guys will need to know throughout this course. Again, y'all should have learned what that was in geometry. And of course, what is the area of a rectangle? We're going to need to use this as well. The area of a rectangle.
Base times height.
Yeah, just base times height. Exactly. So the area of a rectangle is equal to base times height. Okay. Follow me so far? Okay. So those are the two equations for areas that you guys need to know in this course. Okay. Now, here's what we're going to do. We're going to take the area of this velocity versus time graph here, and then in just a moment, I'm going to tell you guys physically what that area means, because that area has a physical meaning to it in terms of our moving object. Okay. So, but first, let us calculate the area. So we know area is equal to, in this case, it's equal to 1/2 times base. I'll put a B for base, and then an H for height. Okay. So you guys tell me here. So this is 1/2. What is the length of this base here? Guys, 5. And what is the length of the height of that triangle?
4.
Yeah, so 4. Everybody follow me? The base is 5 units, and the height is 4 units. So what is 1/2 times 5 times 4? What do y'all think?
Is that 20? I mean 10?
Yes, exactly, because 5 times 4 is 20, and then take half of that, you get 10. But 10 what? What specifically does the area represent? Okay, guys, I'm telling you guys right now, in this course, anytime you see a velocity versus time graph, and you take the area of that velocity versus time graph, it always represents the object's displacement in meters. So I'm gonna put the units here. So okay, the area of a velocity versus time graph always tells us our object's displacement. Of course, we talked about displacement last class period. The area of a velocity versus time graph tells us displacement. Something very important I need you guys to keep in mind. Okay, so guys, what this number right here means is that if we have an object that starts off for rest and speeds up at a constant velocity over a period of 5 seconds, this is how far it's traveled after that time. So when we find the area of velocity versus time graph to tell us that. Okay, so those two things you guys need to remember in this course. You guys need to remember that the slope of a velocity versus time graph tells us acceleration, but the area of a velocity versus time graph tells us displacement. Remember those two things, guys. That's super important. Slope of a velocity versus time graph is equal to acceleration. Area of a velocity versus time graph is equivalent to displacement. Okay. Let us look at a couple more examples. And did everybody follow what I did? Are we good? Can I move on? Okay. Guys, suppose I have a velocity versus time graph that looks something like this. Again, we're plotting velocity along the vertical axis. And we're plotting time along the horizontal axis. So by the way, guys, what does this graph right here tell me my object is doing? My object is doing what? This should be easy.
It's in a constant speed.
Exactly. It's moving at a constant speed of 3 meters per second. Can everybody see that? So it's moving at a constant speed or a constant velocity. Okay. So if I have a graph that's moving at a constant speed, and I take the area underneath this line here, what do I get? Well,
can you repeat that? Oh.
So I'm gonna take the area underneath this. I'm gonna take the area here of this graph. So in order to take the area here, and remember what the area should tell us. The area will tell us basically how far the object has traveled after 5 seconds in this case. So if I take this area here, oh, hold on. Why do I always do that? I used the wrong tool.
You gonna do the area of the little? Is it gonna be a rectangle?
It will. It will be a rectangle. Like boom, boom, boom. Good job, Michaela. Right, you're gonna get a little rectangle here. So if we take an area of a rectangle, it's just what?
2015. Oh, it's gonna be base times height.
Yeah, just base times height. So my area here.
Length times width times height.
Yeah. Yeah, you can either say length times width or base times height, however you want to say that. Okay. And so in this case, guys, right here, guys, what is my base?
5 meters.
No, that's 5 seconds. We're plotting time. Yeah, we're plotting time along the we're plotting time along the x-axis. And my height is what? I heard someone say it. What is my height?
3?
Yes, it is 3. Specifically, 3 meters per second for my units. And of course, what's 5 times 3?
15.
15 meters.
Would it be square?
Nope. It is not squared. In just a moment, Angelina, I'm going to show you why it's not squared. I'm going to show you why it's just meters. Just bear with me. Your units are just meters. Guys, what this is saying is that, guys, this area here. Oh, Angelina, are you thinking of areas from algebra where you do meters squared, like when you take the area of a let's say like a fence or something, that your units are in squared? That's what you're thinking of, right?
Yes.
Yeah. No. We're not. We're no. The how can I explain that? Uh, so in in the case of algebra, like let's just say you're dealing with perimeters and areas of fences. In that case, you have the same units on both your y-axis and your x-axis. So let's say you have meters on one axis and meters on the other axis. Then meters times meters gives you meters squared, okay, which is not what we're doing here. Hope that makes sense.
It does. Thank you.
Yeah. That's actually a really good question. No one has ever asked it before. Yeah, yeah, and yeah. I'm in a moment. I'm going to show you why the units are in meters when you multiply the two. Uh, but if this was like, let's just say, if this was like someone's yard or something, and you were finding the area of that yard, where you would have meters here and then meters here, then it would be meters squared. But that's not what we're doing here. We're plotting velocity on one axis and time on the other axis. So the concept is different. Everybody else, does that make sense? Did everybody understand what Angelina was asking? That was actually a good question. Everybody got that?
What she asked?
Yeah.
She was thinking the units were meters squared because in your math classes, whenever you take areas of like let's say some region of space, then it is meters squared because you're plotting meters on one axis and the meters on the other axis. But that's different than what we're doing here.
Well, I didn't know that.
Yeah, that was actually a really good question.
I didn't pay attention to that.
Huh?
Nothing.
But for now, everybody understand what this is saying here. So if I have a velocity versus time graph, and I take the area, which is just basically me shading this whole region here, the area here would be meters. And so, guys, what this is telling me, is that if I have an object that is moving at a constant velocity of 3 meters per second, and it travels a total of 5 seconds, then its overall displacement will be 15 meters. That's what this area physically represents. It represents the object's displacement. Let us look at one more example. So suppose I have a velocity versus time graph that looks like this. And guys, what is my object doing here? In the real world, if this was describing a real world object, what's going on here on this velocity versus time graph? My velocity is not constant here.
Slowing down the negative direction.
It is moving in the negative direction, Michaela, but it is not slowing down. Jeremiah is right. It is accelerating.
In the negative direction.
Yeah, it's accelerating. It's speeding up in the negative direction. Michaela, remember, it'll be slowing down if it will be approaching zero. Do you remember that?
Yeah, I got it.
Yeah, this is going further away from zero, so this is speeding up. So this speeding up in the negative direction. Okay. Now, guys, so if I have an object that starts off with an initial velocity of 0 meters per second and accelerates for 4 seconds at this rate of acceleration, how far does it travel over time? Well, that's what the area of the velocity versus time graph tell us. The area will tell us our object's displacement. So if I take this graph right here, and let me take the area of this graph at 4 seconds. So, obviously if you just, do that here and then here. Notice, guys, you get you a triangle. And so if I shade in that region, I would get something like this. And once again, how do I find the area of a triangle?
You have to do like times height and then like a fraction or half.
Yeah, 1/2. Yep. Times base times height. Okay. So 1/2. So guys, what is my base here? What is the base? Or in other words, what is the length of the triangle?
Two.
No, that's the height. Remember, the base is along your horizontal axis. Height is along your vertical axis.
Where are you getting these numbers from?
look at count the grid points, Jeremiah. 1, 2, 3, 4. So your base is 4. In this case, is 4 seconds. Does that make sense, Jeremiah? I'm just counting the grid points.
Oh, okay. I have to zoom in.
Oh, you can't see these grid points on your computer? Makayla, what do you mean you can't hear anything?
I don't think she couldn't hear you say that. She can't hear anything.
Oh, you're right. Good point.
So you said the base is 4?
Yeah, the base is 4. Does everybody see why the base is 4? Guys, just look at your grids. Here's 4 units, and my height is what someone said earlier. My height. Yeah. Was that you, Aaron?
Yes.
Okay, thank you. Yeah, you're right. It is 2. Yeah, so my height here. So remember, the height is along the what's along the vertical axis, and so now it's just not 2. It's -2. Yeah, because I'm counting in the negative direction. Here I'm counting the positive direction. Here I'm counting the negative direction. So, what do I get here when I multiply? What is my overall area?
So that would be -4.
Yep, it'd be -4. Specifically, -4 meters. Okay. So in other words, if this graph is explaining an object that is speeding up in the negative direction, what that number means, that number represents my object's displacement. So in other words, guys, what this is saying is if I have an object that starts off at rest, so let's say this is a car here. The car starts off at rest and the car hits its accelerator and begins speeding up while moving in the negative direction. So if it speeds up over the course of 4 seconds at a constant rate of acceleration, then after that time, this is how far I would have traveled. It would have traveled a total of 4 meters. That is its overall displacement. And again, the negative just means we were moving in the negative direction. Again, so we had a displacement in the negative direction. Does that make sense, guys? Please remember that, guys. If there's something that you guys, if there's one thing that you embed in your brains before you leave the Zoom session for today, remember that the slope of velocity versus time graph tells us acceleration. But if we take the area of a velocity versus time graph, that equals displacement. I'm going to say this again. Slope of a velocity versus time graph is equal to acceleration. Yes.
So, is that a -2?
That is a -2. Yeah.
Can you explain why it's negative again?
Well, look at your graph. Is my graph, is it on the negative end or is it on the positive end?
The negative end.
The negative end. Yeah. So okay. when it was above this line, what's on my vertical axis was positive, but below that line was on there is negative.
Okay, thank you.
You're welcome. Okay. So hopefully that makes sense, guys. I'm gonna repeat that one more time. I know I keep repeating myself, but that's important. Anytime you have a velocity versus time graph, the slope of that graph tells us acceleration, and our units are in meters per second squared. But if we have a velocity versus time graph and we want to take the area of that graph, that tells us displacement, and our units are in meters. By the way, I want to prove to you guys why the units are in meters for a velocity versus time graph, and I'm gonna prove that to you guys right now. Oh, let me erase this here. So let me give myself some room here. Okay, so guys, I want to prove to you guys right now why is it that whenever you take an area of a velocity versus time graph, you always get your result in meters. Well, again, the area of a rectangle is equal to base times height. Well, what did we just say for hold on, let me fill out my axis here, and then I'm gonna ask the question. Hold on, give me just a second. So this is a velocity versus time graph. Okay. So again, along this horizontal axis, which is our base here, what are we plotting? What units are we plotting, guys, along this horizontal axis?
Seconds.
Seconds.
Meters.
Right? Seconds. Yeah, because time, guys, along the x-axis, we're plotting time, and time is always in seconds. So I'm gonna write an S there to represent seconds. And what are we plotting along the vertical axis? What are our units along this vertical axis? What are the units for velocity along the vertical axis?
It's not meters per second?
It is meters per second, yeah. So along my height here, I'm plotting meters per second. Okay. Guys, you all should notice something. If I multiply seconds times meters per second, what cancels?
The seconds.
Yeah, the seconds cancel. And what am I left with?
Meters.
Meters. So there you guys go. That's the proof that anytime you take the area of a velocity versus time graph, the area always represents the object's displacement in meters. Okay, right? Because seconds times meters per second, the seconds cancel, right? And again, guys, this y'all know this from algebra, right? It's kind of like in algebra, guys. It's just like in your algebra class. It's the same thing as multiplying 2 times 1/2. If you take 2 and multiply that by 1/2, what does it give you? It just gives you 1, right? Because if you multiply 2 times 1/2, notice the 2's cancel, right? And you're just left with 1, right? So, right. Another way of saying that, if you have 2 halves, that's equal to a whole. Like 2 of 1/2 is equal to a whole. The 2's cancel and you're just left with 1. That's what I did there. I just did that in terms of my units. Any questions? Okay. So everybody got that? Anytime you take the area of a velocity versus time graph, your units will be in meters. Okay. Always. Okay. Well, assuming you're plotting meters per second here along the vertical axis and seconds along the horizontal axis. So basically your base times your height. Is all of this making sense, everyone? Okay. So I'm gonna stop sharing my screen. Now, before I go today, let you guys go for today, I want to talk a little bit about how you can figure out the acceleration of gravity. Now, can someone tell me, here on Earth, if you take an object and you drop it, what is its rate of acceleration?
8.9.
It's what?
-9.8.
8.9.
-9.8.
Macaulay, no, Macaulay's correct. It was correct, Jeremiah. It's 9.8, yeah. So negative 9.8 meters per second squared is the acceleration of gravity. Y'all, that is an important number y'all need to remember. An important number. It's so important, I'm gonna put it in the chat box. So acceleration of gravity here on Earth is negative 9.8 meters per second squared. That's an important number y'all need to remember. Negative 9.8 meters per second squared. Never forget that number, guys. Okay. If I see you all 10 years from now, if I run into you in Walmart or something, and it's 10 years from now, and I ask you, what's the acceleration of gravity? You're going to have to tell me just like that. Because I'm going to ask if I run into you.
I'm not going to be an astronaut in 10 years.
Don't matter. I want you to remember that number. And there's a good chance I can run into you in Walmart, right, Jeremiah?
Ironically.
Because if I run into you, I'm going to ask you some physics questions. All right, now, so guys, in the past, during a normal school year, believe it or not, I actually have my students prove that the acceleration of gravity is 9.8 meters per second squared. And guys, I want to spend the next 3 or 4 minutes or so walking you guys through how I have my students to prove this out. Like during a normal school year, in a normal class setting, when we can do labs and activities and stuff, I have my students prove this. But for now, I'm just going to show you guys. What we do, the first thing that I would do, I would show them this video here. Let me share my screen. And again, this is how we prove the acceleration of gravity. It's 9.8 meters per second squared. Okay, so guys, look at this video here of this physics teacher dropping a yellow ball. Okay. So, and again, sorry is sideways, but you guys can still see what's happening. Okay, so he's going to drop this yellow ball, and guys, it should be clear to you that as the ball falls, the ball is clearly accelerating. Okay, so the ball is clearly speeding up. Before it hit the surface of the earth. Now, guys, here's what I do typically during a normal school year. I would have my students watch this video here, and I would tell them to look closely. I would tell my students to look closely at the ball, and watch the ball falls. And we typically watch this video frame by frame by frame, because we want to note the position of the ball at each frame. Notice this is 310 centimeters. This will be 170 centimeters all the way down to the bottom. So basically, we would watch this video. We would watch that. Michaela, this mug is lagging hard. That's so ghetto. Anyway, so we would watch that video, and we would look at that frame by frame by frame. And here's what I would have my students to do. Let me show you guys. Let me pull up the PowerPoint. I actually like this activity because, as soon as my students get done with this activity, they would approve themselves that the acceleration of gravity is 9.8 meters per second squared. I'm really sad that we're not going to get to do it this year, but it's okay. I can just still show you guys. So guys, that video that I just showed you guys, here's the video analyzed frame by frame by frame. Notice the initial position of the ball. The initial position of the ball is somewhere around 316 centimeters, which is 3.16 meters. And notice how the position of the ball changes as we play the video frame by frame by frame. By the way, can you guys clearly see that the ball is speeding up as it moves from top to bottom? Can y'all see that it's accelerating? I'm going to do it again. And guys, it's accelerating because remember on a motion map, as it accelerates, remember that the spacing should get far and far. It should get farther and farther apart, every second. Every frame, I should say. And we clearly see that for every frame, the ball is clearly accelerating. It's speeding up. So what I would do, guys, I would have my students to write down the position of that ball for every frame. And then I would tell them, okay, knowing the position of that ball at every frame, is up to you to calculate the acceleration of that ball. And I would give my students this blank sheet of paper here. Let me show you guys how the blank sheet of paper looks like. So I will give my students this blank sheet of paper here. And guys, those position values that we just looked at, I will have my students to literally fill out the position of the ball at every frame as it falls. And of course, there was a total of 16 frames in that video. Okay. And by the way, by the way, guys, each frame is approximately 3/100 of a second. So, frame by frame by frame, the ball is falling. And then from here, guys, I will have my students to calculate the velocity of the ball at every frame. And guys, y'all know the equation for velocity. We talked about that this second week. The equation for velocity is change in position divided by change in time. In other words, is final position. Hold on. Let me make this bigger. Let me make this bigger. So the equation for velocity is equal to final position minus initial position divided by the time interval, or delta t, the change in time. Okay. So guys, using this equation here, once the students have the positions, they literally put the velocity of the ball frame by frame by frame. They do the calculations each frame until they figured out the velocity at all, after all 16 frames. And then from there, I asked my students, okay, after you calculated velocity, now I want you guys to calculate acceleration. And so the equation for acceleration is equal to final velocity minus initial velocity divided by change in time. So using this equation here, once they have velocity values filled out here, my students would then use this equation to calculate the acceleration of the ball. And guess what they get, guys, when they compute the acceleration? Guess what number pops out here? I just said this is the acceleration of gravity, which is...
I got to think about this one.
It's 9.8.
9.8?
Yes, thank you, Angelina.
Negative.
Yeah, they literally get a negative 9.8 meters per second squared. And again, guys, this is typically what we do during a normal school year. Whenever I have you guys in class and we can, practice this activity together. And I like doing this activity, guys, because this activity proves to all of my students that the acceleration of gravity is 9.8 meters per second squared. I like it because you guys figure it out yourselves. And of course, guys, the key thing to know is that the acceleration is constant. Understand what I mean when I say a constant acceleration. So the velocity is changing, but the acceleration remains constant. For example, how do I show the velocity of the ball is changing? Well, guys, let me share my screen here because I want to show you guys the exact value that my students get when they calculate the velocity of the ball at each frame. So we clearly see the position of the ball, but then after we do the math, we literally find the velocity of the ball at every second. Well, not every second, but every frame, which is every 3/100 of a second. So, and guys, can y'all clearly see that the velocity of the ball is increasing? It's getting faster and faster and faster. So notice how the velocity starts off somewhere around 2 meters per second, and then by the time the ball is near the bottom, it's moving somewhere around 7 meters per second. So the velocity of the ball clearly increases. But once we take these velocity values, we then calculate acceleration, and exactly as a couple of you guys say it, the acceleration. Oh, Lord, I just realized y'all can't see my screen. Hold on. So as a couple of you guys just see it, hold on, let me. Once we calculate the acceleration of the ball, we notice that the acceleration stays constant at 9.8 meters per second squared. So that's how I prove to you guys the acceleration of gravity is this negative 9.8 meters per second squared here on Earth. Again, you guys don't have to worry about going through those calculations. You can if you want. If you want to do it on your spare time just to see if you get 9.8 meters per second squared, I would gladly recommend that. because it's always cool to prove it to yourself. Um, but anyway, guys, as soon as I am done with that, I have my students to do one more step on that assignment. Here's what I ask my students to do. I ask my students to figure out. Oh, let me put back on the screen. I ask my students to figure out. Okay. Hold on, guys. Let me. So the last thing that I ask my students to do, once they figured out the velocities of the ball, the velocity of the ball as it falls frame by frame, I then ask my students to calculate the displacement of the ball. So if the ball starts off from this point right here, and it falls and drops all the way to this point here, I then ask my students, guys, mathematically figure out the displacement of the ball without looking at these numbers here. How can you figure out the displacement of the ball from here to here using a velocity versus time graph? So in order for my students to do that, here's what they do. They first graph out all of these velocity values here, and they put them on a graph, and this is how the graph looks like. Okay. So guys, here's an actual graph from one of my students last year. Her name was Cameron. She was in my 7th period class. That situation that we just saw, where the ball was falling from top to bottom, I will have my students to plot out the velocity time graph of that object, and this is what they would get. So they would, let me zoom in here. They would literally put dots, for each frame to represent the velocity of the object, and then once they have their dots, they then draw a best fit line through the data. Okay, and hopefully everybody should be able to clearly see that this graph here that my student last year made, it clearly shows an object that is speeding up in the negative direction, which is clearly what the ball is doing. The ball is speeding up as it's traveling in the negative direction. Okay, now guys, I asked my students, if you have this velocity versus time graph, how can we figure out the displacement of the ball from this graph? Well, what do we do, guys? We talked about that at the beginning of the class. How do we figure out displacement from a velocity versus time graph, y'all? We do what? We look at the what? How do we take displacement from a velocity versus time graph? Come on, y'all, wait.
Find the area of the triangle.
Thank you, Stephanie. We find the area. Exactly. We find the area. Now, Stephanie, here in this case, you're going to actually have a triangle and a rectangle. I'm going to show you what I mean by that. Hold on. Let me hold on, guys. Let me pull this up in Kami so I can annotate it. Hold on, guys. In just a moment, I'm going to get ready to share my screen with you all. Sorry, I should have pulled it up in Kami the first time. I don't know about what I was thinking. Okay, so yeah, so exactly as Stephanie said, we want to take the area of this line. Now, guys, that entire video played for about half a second from the time the ball was released to the moment that it fell and hit the ground. So we're going to look at 0.5 seconds, and we want to figure out the displacement of the ball in 0.5 seconds. In other words, this right here, 0.5 seconds, is going to represent, our stopping point. Okay. And then once we take the area of this line, and again, guys, the reason why I like this is because this is real world data. My students actually got this from that video. So if you guys notice, we have a rectangle here. So we have a rectangle here. Okay. But in addition to that rectangle, we also have a triangle. I want you guys to notice that there's also a triangle here. So there's a triangle here. So guys, I would have my students in the past, okay, I want you guys to look at this graph here, and I want you to mathematically tell me what is the area of this rectangle. And then as soon as you're done with that, mathematically tell me what is the area of this triangle here. Okay. And then once you have both those areas, I want you to combine them, add both those areas together to get the total area of this region. And guess what? The total area of this region, when my students find this, it turns out that it precisely matches the displacement of the ball as the ball travels from top to bottom. Okay. Like that area of that velocity versus time graph matches the displacement from top to bottom. And again, I like this assignment because it's actual real world data. The students actually get to see that, that the area of a velocity versus time graph is equivalent to the object's displacement. Okay. Any questions? Any final questions before I explain you guys' assignment? Okay, now, here is your assignment for today. Okay. So guys, your assignment is going to be slightly different compared to the past. In the past, I just uploaded an assignment into Schoology. But for today, you guys are responsible for doing the progress check assignment in AP Classroom. So let me show you guys how to get to that. Okay, everyone in here, whenever you're working your assignment, you're going to log into your College Board account. So you're just going to go to myap.collegeboard.org. Okay, so myap.collegeboard.org. You're going to enter your username. Okay. Then you're going to enter your password. Okay. And then guys, once you are in, you want to go to AP Classroom. Okay. Okay. So guys, in AP Classroom, I have assigned every class to complete the Unit 1 progress check. And all you have to do is the Unit 1 multiple choice progress check. You're not doing the free response questions. You're just doing the multiple choice questions. Okay. Now, guys, these progress checks, they cover the entire unit. They cover the entire kinematics unit. And basically, guys, it is 16 questions, all multiple choice. Okay. In addition to it being 16 questions, all multiple choice, the test is also timed. Well, it's not really a test because it's not counted as a test grade. But it is a test in the sense that these questions look very similar to the types of questions you're going to see on the AP exam in May. Okay, so this assignment is timed. You are given a total of 24 minutes to do a total of 16 multiple choice questions. So you guys are going to have to get in the habit of pacing yourselves. Okay, you're given 24 minutes to do 16 multiple choice questions. Guys, everyone must complete this progress check before tomorrow at 11:45 p.m. Okay. If you are not done by tomorrow at 11:45 p.m., AP Classroom will lock you out and it just submit what you already have. So let's say you get on at 11:40 and you didn't finish. If you only have 2 problems answered, then that's what AP Classroom is going to submit. So it's going to lock you out at 11:45 p.m. No exceptions, guys. So, guys, you have today and tomorrow basically to get this done. And of course, this has to be done by tomorrow because my AP coordinator, she's looking for these results. I have to basically report these results to her by Friday.
How many questions is it?
There are 16 multiple choice questions.
Okay, thank you.
And you have 24 minutes to complete it. Okay. Now, I'm telling you guys right now, these are not easy questions. Okay. These are some very difficult questions. AP Classroom asks hard questions. So just to put this into perspective, guys, keep in mind, I don't know if you guys know this or not, but on the AP exam, the actual AP exam is so hard that if you score somewhere around a 50%, that is enough to pass the test. A 50% or higher will give you a passing score on the AP exam. Okay, so I'm telling you guys right now, whenever you guys are working on this assignment, if you score at least a 50%, I consider that to be good. In fact, I consider it to be excellent because these are some really hard questions. So 50%, that is excellent. Okay. Now, just so you guys know, guys, any assignment that I post on the College Board website, I cannot use these assignments to hurt you. In other words, I can't put a bad grade in the grade book if the assignment comes from the College Board website because these questions are hard, and the College Board knows these questions are hard, so they don't permit me to put a failing grade in the grade book from these assignments. So the only thing that I'm allowed to do, I'm allowed to use this to help you. I cannot use these questions to hurt you. Okay, but I want you guys to do your best because the better you do, then the more of your curve will be on the test. Okay, so I'm gonna add points to your next test grade proportionally according to how you guys do on this assignment here. Everybody got that? Any questions?
Yeah.
Again, these are some hard questions. These questions can't hurt you; they can only help you.
One of my friends just sent me one of the questions. I don't know what it's talking about.
What do you
They
mean
were asking for help.
she sent you one of the questions?
It's a he. He just sent me a question and asked me
Is
for
it who I
help.
think it is from third period?
No, it's actually no, it's somebody else.
Okay, he shouldn't be asking for help because this is a test. And
I don't know
why
what to do anyway. He's
why
looking
is
it up.
why is he sending questions on a time test? Because once those 24 minutes are up, he's locked out.
That's what I'm saying. I don't know. People are slow.
Okay. So Stephanie, you will know your score because I'm gonna let you guys know. Um, um, I'm gonna let you guys know. I don't know how I'm gonna do this. That's actually a good question. In class, I would typically tell my students. I think Stephanie, I believe it tells you your score when you're done. Yeah, Stephanie, you're gonna know your score when you get done with it. I'm like 80% sure that your score is gonna pop up when you're done. Christine, all you do Christine, I don't know what you guys see from your end. All you do is just log into AP Classroom. Do you have a College Board account, Christine? Once you log into your College Board account and you click on AP Classroom for my class, you should see the progress checks. Do you have an account, Christine? Okay, yeah. Just if you want, Christine, you can. When I let everyone go, you can stay on the call, and I can walk you guys through it. Basically, I'll let you share your screen, and I can walk you how to get through it, how to get to it. But it shouldn't be too hard. Any questions before I let you guys go? Okay. Remember, guys, do your best, because as soon as I'm done with um, um, well, as soon as you guys are done working on this progress check, I have to I have to put all the scores in a report and send it off to my EP coordinator. Um, it's just something that they're requiring us to do this year. Okay.